is at 4. We'll see if it's the same. If any of these things fails, not continuous. So limit of this expression as x goes to 4. What do you want to do? Just try to plug it in. First thing, just see what happens. Why don't you plug it in the top? Finite value, 18, right? Non-zero value at the top. What's the bottom do? Heading towards 0. 36 minus 36 is 0, right? Heading towards 0. Now, the top is heading towards non-zero. Bottom heading towards 0. So therefore, what's the limit? D and E. Problem's over. It's not continuous. Right? Not continuous at x equals 4. Agreed? What's going on there? Why is it not? This one was a hole, right?
Isn't that one an asymptote?
An asymptote, right? You got it. It's called an infinite discontinuity. An asymptote, infinite discontinuity. This one's called a removable discontinuity. A small hole like this is removable. Yes, we do a slightly different question. What if it said x equals 3 instead? It said x equals 4. It said x equals 3 for fun. Now what happens?
Plug it in.
What's that?
Plug it in again.
Okay, plug it in. Let's see what happens in 3. Do we get a finite limit or not? 3. Okay, the top is what? 13. What's the bottom? 3. 2. 1. 13 halves. Okay? 13 halves. So the limit exists, right? What is the function at 3? How do you find the function at 3? Plug it in. It's remarkably similar to what you just did with the limit. Don't get confused, right? Remarkably similar. So that answer has to be what?
13 halves.
Yeah, 13 halves. So are they the same thing?
Yeah.
So therefore this function is continuous at 3. Okay? Try one more. 5. Okay. All right, 5 instead. First find the limit. As x goes to 5, what happens to the top? Heading towards 23? 23. What's the bottom heading towards? 0, right? 45 minus 45, 0, yeah? So we're heading towards non-zero, meaning finite non-zero, over 0. Therefore, you guys are getting sloppy, look at you.
D and E.
D and E. D and E. Not continuous there. Not continuous in 5. Right? Same reason, asymptote. Those are our 2 asymptotes, at 4 and at 5. That's why it's not continuous there. It's continuous everywhere else. Right? Every other point. Yep.
Can't you have backed up the bottom to get 4 and 5 also?
You can.
Okay. But does that work all the time, or?
I mean,
Yeah. That's where I was coming. That's where I came with the 5. I knew how it factored. I picked another number was going to fail. Now, the usual reason you factor it, though, is to try to cancel with the top. In this case, it does not happen, right?
Yeah.
Yeah. Now, they gave us the 4 to start with, right? We didn't come up with the 4. They gave us the 4.
Yeah.
Yeah. That's correct. All right. What's that? Okay, now we said that, I will tell you some more overarching principles about continuity. If your function is a polynomial, I'll just sweep it all, or an exponential function, or a logarithmic function, or a rational function, or a root function, or a trig function, then P is continuous. You gotta be careful with this one caveat at the bottom. Everywhere is defined. Everywhere is defined, it's continuous. Everywhere is defined. Doesn't mean it's continuous everywhere. Now, polynomial is. Polynomial is continuous everywhere. And so are exponentials. Okay? The other one's sine and cos are. Everywhere. Okay? I mean the whole real line is what I'm trying to say, right? When I say everywhere, I mean the full breadth of the x-axis. Now the other ones, logarithmics, rationals, and the other trigs and the roots, they are continuous wherever they exist. There could be asymptotes, they don't exist there. So they're not continuous there. But anywhere they exist, they're continuous. So what are we really eliminating? We're saying there's no holes with dots above them or below them, right? Because you can have functions that exist, right? They exist there, but it's not continuous there. All of these functions, wherever they exist, there's no way it's this case, right? The dot is in the hole, in a sense, okay? That's for all of them. These three, though, include the whole real line. So, just for example, let's take a logarithm. We just said it was something like this. So, what's its domain? What's the domain of like an ln of ln x? What's the domain of ln x? Well, according to the picture, it is all positives, right? It's all positive values. Okay? That's where it exists. So it's continuous for all positive real numbers. Is it continuous at 0? No, it's not a positive real number. Is it continuous at -5? No, there's nothing even going on at -5, right? But wherever this little puppy exists, he's continuous. All right? Tan. We just drew it a second ago, and I'm picking it again because I want you to remember it. Right? Negative pi on 2. Pi on 2. There is our cute little picture, and we know it repeats every pi like I just said a minute ago. Right? Great. Tan has asymptotes at pi on 2 plus k pi. Right? That's where he does not exist. So is tan continuous at pi on 2? No, because it doesn't even exist there. Is it an asymptote? Yeah, I don't care if it's an asymptote. I don't care. It's a whole, I don't care what it is. It doesn't exist there, so not continuous. But anywhere he does exist, is he continuous at 0? Yeah. 1? Yeah. Pi on 4? Yeah. You know what I'm saying? Anywhere he exists, he's continuous.
That's what you mean by everywhere it's defined?
Yeah.
Okay.
That's right. Its domain. On its domain. Everywhere it's defined means on its domain. So you have to know, you can't just say tan is continuous everywhere. It's not true. It's continuous on its own domain. Its domain does not include the asymptotes.